The theme in my group is how to use crystal chemical tailoring of materials, really tuning them to get properties that give you very good energy conversion technologies. And the key one that we're focusing on is certainly fuel cells, but there are other things of interest: thermoelectrics, thermochemical materials, and so on. So those are areas that are not main focus, but it really is, how do you create new materials that have the properties that you want, with the focus of properties that you want being in the energy conversion arena. We're trying to discover and optimize materials that have very rapid ion transport, and so that plays into fuel cells, because you need, in a fuel cell, an electrolyte that has very high ionic conductivity. So ions have to race across this material, and that's not a typical feature of a material. In the case of the electrodes for a material, then we want materials that not only have this rapid ion transport, but also have very good catalysis and very good electron transport. So now it becomes an even more complicated set of requirements. So all of that has to do with understanding how it is that ions and electrons can move through solids. I would say that over the years, I've always been interested in ion transported solids, but I've selected those materials that have a closer relevance to an application. So there are exotic materials that have very high ion transport, but may never end up in a real fuel cell or any kind of device, simply because there are other characteristics that are undesirable. So sort of those materials that might be considered model systems for whatever scientific reason, those have had less airtime in my group as the years have gone on, to be, as our whole need for sustainable energy has been growing tremendously. University research, by definition, is fundamental. By definition, we don't make devices that you can go off and sell. And I think this is a very hard idea and an unfortunate consequence for the business community and maybe the public to appreciate, is that there's a big step between making a fundamental breakthrough in the laboratory and making a device that you can go buy at Sears. And that is a huge range of activities that go on there. How do you develop the manufacturing protocols to actually make this cost effective? Not only because the materials inherently might be cost effective, but the processes of making this complete device. It's not that daisy chain in the sense that you go from one academic setting to the next. I would say that you go from our academic setting to some sort of commercial entity that is going to say, okay, you have all the basic components in place, you've shown that the ionic conductivity is sufficiently high, the electric catalysis is sufficiently high, that the material stability is sufficiently good. Now, how do we actually make the device? And that's not an academic enterprise. Yeah, so we have a horizontal monopoly, I would say, as opposed to a vertical monopoly, which is, to take it forward to commercialization. No, it's true that there, in many devices, many different components. So again, in a fuel cell, you need an electrolyte, you need an anode, you need a cathode. So we work on all of those in the sense that we don't rely on university breakthroughs at other institutions to give us the great cathode that goes in our fuel cell, or give us the great anode that goes into our fuel cell. We do attempt to cover all grounds. It's not to say that we're the best in all three arenas, but we definitely do that in some regards, because the electrolyte that we use is distinct, especially in the presentation that you heard, which is the solid acid electrolytes. It is an electrolyte that nobody else really studies. So that means we have to develop the auxiliary components, the anode and the cathode, in-house, because it's just so different from everything else. Well, again, as I mentioned, there's this overall objective, which is to operate fuel cells at a moderate temperature regime. Okay? It gives you this great benefit of great catalysis without the drawback of horribly expensive high temperature materials. And we do that like nobody else can. I mean, we are in the sweet spot of temperature. And this is because, a bit of serendipity. 12 years ago when I was in Germany, I came across a material set that nobody else in the US was looking at. It was sort of come out of some very early Russian work. Russians are interested in phase transformations. This is, in crystallography. This is historically a Russian expertise. Came across these materials, realized these were very high proton conductors, and like I said, spent some time just really trying to understand the crystal chemistry. Why do some materials have this high proton conductivity and why others don't? And having done this, wait a minute, I go to these fuel cell conferences and they're all saying, oh, we can't get our polymer to work because of X, Y, and Z. Oh, we can't get our solid oxide fuel cell to work at low temperatures because of X, Y, and Z. And we're sitting on the most potentially remarkable material possible. We never actually tried it in a fuel cell just because it was kind of fun, to look at the proton conductivity. Tried it in a fuel cell and it worked great. I mean, of course, not on the very first try, and there were things to be solved. And this is why we continue to do materials discovery efforts, because there are still some challenges. But found that it works great, and so that's the spawning of it, why we end up making a company out of it.